So we've covered atomic spectroscopy, starting with the electron configurations, the Grotrian diagram. Then we got into electronic spectroscopy of molecules, where we ended up looking at the Jablonski diagram. And then today we're going to be sort of taking a side trip to talk about lasers. So we've already discussed how a laser uses stimulated emission. That's the SE in laser. And so today we're going to really unpack how we get the stimulated emission setup. Okay. So in discussing lasers, we're using that line spectrum, typically of atoms. They make molecular lasers, but the first lasers were using atoms because they have that real, what we call spectrally bright emission. So you get, enough energy into these atoms, and they put all of that energy when they emit it in a very narrow region. So it's incredibly efficient. They're shooting all of their light at a particular wavelength, plus or minus a very small amount. And so you'll hear me use phrases like line spectra and continuum. So I just want to emphasize that again. This is a continuum. You get the full rainbow. You get all of the wavelengths of light as a continuum. Up there is a line spectrum, an emission of particular wavelength. In this case, it's 632 nanometers for the helium neon laser. Now, helium neon lasers are red. Let's see, do I have a laser pointer in here? Yes. But the laser pointers on like these little laser pointers is red too, like you can see there. But this is a diode laser on here. So this isn't a helium neon laser, even though it's red. So not all red lasers are helium neon lasers. A helium neon laser is a gas laser, so you've got to have a little gas chamber with mirrors on both ends. And so we'll look at that in a second. So these are all the different, you have tons of different colors for lasers. These are all, well, they may not all be solid state lasers, but many of them are. Solid state lasers and diode lasers are the same thing. So we've discussed the Jablonski diagram, and so we would be looking for lasers that are using, these lasers are going to be using fluorescence, so not phosphorescence. We need an efficient emission of light, and we need those selection rules to be allowed. So these lasers are using the fluorescence signal in some manner. And so this is how we get stimulated emission to be probable. Okay. In most cases, we have this thermal population or thermal equilibrium given by the Boltzmann distribution. And the Boltzmann distribution, is e to the minus e minus e0 over kt, right? So when we're at e0, it's essentially a probability of 1 that we're going to be in the ground state, and then it's going to be a smaller probability that we're in any of the excited states. Okay. And so this is why thermal equilibrium almost always has more molecules in the lower states than the upper states. The only way that can change that really is this piece in front, which will be the degeneracy factor. We have that G factor in the front. So that's Boltzmann. It's a function of the quantum number and the temperature. Okay. But if we have, like in this case for the neodymium YAG laser, it's a neodymium atom in a crystal of yttrium aluminum with the garnet shape. The crystal shape or crystal type is a garnet crystal made up of yttrium and aluminum. So that's the YAG part. And then we take out some of the yttrium atoms and we dope in some neodymium atoms. So the neodymium atoms are in a very uniform environment. And when they have a uniform environment, then all their energy levels are very well defined. And so we pump that neodymium atom, and we get some of them in the excited state. And the pumping isn't perfect, so some of them get pumped up and they go back down to the ground state, but some of them get up there and then they fall into this metastable state. Now, why do we have all these 4 energy levels? Well, look where neodymium is. It's over here, number 60. It's in the F block. So its energy levels are all over the place. Remember when we were doing electron configurations, we didn't go to the F block, okay? So there's, in terms of what these energy levels are, I don't know. I'd have to go look them up. I'd go to the NIST Atomic Spectral Database and pull up the Grotrian diagram, and I would see these energy levels. So, but this is the lower energy levels for that neodymium atom. We're pumping it with visible light, and we're getting atoms in that excited state. And you see it's like a pump. So we pump these atoms up, and then they start to fall down, and they hit this one, and then this is fast relaxation. So this area right here is the area where the laser is going to be. That's going to be the population inversion. So once we have pumped these atoms up into this excited state, you see they start to build up. And so then we have this setup. This is how we have the laser setup. We've got the visible light. This is the neodymium laser rod, and we're pumping with visible light. We're exciting that rod, and we end up with a population inversion. You see all of those green atoms are in the upper state, and there's none here in the ground state. So that's inverted, right? Inverted relative to the Boltzmann distribution. The Boltzmann distribution would want more atoms in the ground state or lower states, but this is inverted. That's the key to a laser, is having a population inversion. Now, what happens is one of those atoms falls down and spits out an infrared photon. Okay? And then that stimulates the emission of a second atom that dropped down. And now we've got two photons that are in phase with each other. So if you think of light as a wave, now that wave has twice the amplitude. Or you can think of that as two photons with the same wavelength. But it helps me to think of a coherent wave, like a standing wave. It starts out with the first emission, and now the second emission is in phase with that, so the wave got twice as strong in terms of its amplitude. It's the same frequency. That's the wavelength that, what's nu, C over lambda, that's the frequency wavelength, that's fine. But it's the amplitude is how bright it is. Okay, so it's twice as bright. Now another one pops down, and now it's 3 times as bright as the first one. And so we just keep getting brighter and brighter, and that's why these lasers are so bright. They're all emitting at the same wavelength, and the amplitude of that wave is getting super strong. Now, if we want to do spectroscopy with this, that's great, because the oscillating electric field is the amplitude of that electric field. If we want to see if a molecule is going to vibrate or the electron cloud is going to do something, we need a light source with a huge amplitude so that we can excite the electron cloud or the vibrational mode or whatever. So lasers are great for spectroscopy because they have a very narrow wavelength, a very specific frequency, a huge amplitude that can cause our science to do what it's supposed to do. Raman scattering, absorption, those kinds of things. So that's the 1064 nanometer light that comes out of a neodymium YAG laser. And it's solid state too. So it's got, solid, this rod is solid. We can have maybe LEDs instead of like a flash lamp or anything. We can have some visible light source to pump that rod to get it pumped up into a population inversion. Now, how can we build this up even more? We can put it in a resonant cavity. So we can have a front mirror and a back mirror that is some multiple of the wavelength of light. So the distance between those mirrors can set up a standing wave of light in that cavity. And if we do that, then the photons may come, like let's say that first emission was right here at the face of this crystal. It goes down here, bounces off, and comes back, and now it can go through the rod and cause stimulated emission. And so maybe it causes 5 more stimulated emissions. Well, maybe we want it to go back again. So we come back, bounce off of this mirror, and come back. And because these mirrors are certain, like integer multiples of the wavelength, it's still in phase when it comes back. So it bounces off that mirror, comes back, it's still in phase, and it causes the more drop down, stimulated emission, and it gets bigger. So that's the light amplification by stimulated emission of radiation. So this is a resonant cavity. It would just keep building up and building up and building up. But if we want to let the light out, we take this front one and we we make it a mirror, but not 100% mirror. We might just do a 50% mirror. So half the light leaks out over time. And so that's how we build a laser cavity. You can think of it as a resonant cavity where we respond pretty well with sound. If you have take a bell and ring it, you hear it ring, you put a piece of gum on the side and it doesn't ring as well, right? You hit it and it doesn't ring. You take that gum off and it resonates. So that's kind of what we're thinking of with light. If the mirrors are off a little bit, it won't resonate very well. But if you get it just right, you tune those mirrors, then the light is efficiently amplified and it comes out as a laser. Okay. Now, this is lasers, because they put all their energy in particular directions, they can be dangerous. The very smallest or lowest power lasers are class 1. They go class 1 through 4. Class 1M is safe, but don't look at it with a magnifying glass. Class 2, this is, I can't read that. What does it say? Class 1, okay. So this is a class 1, safe for all uses, so it's eye safe. So that doesn't hurt. It's pretty weak. This is a pretty weak laser pointer. See, that's not very bright. I had one that was much brighter. It was a class 2. And it's listed, it says don't stare into the beam. So don't just do this. Okay, because you'd be pretty stupid to do that anyway. But it's also listed as mildly irritating. And so you hit yourself in the eye with a class 2 and yeah, it makes you want to blink. This one doesn't really even make me want to blink. Okay, so y'all can be texting or posting. My professor keeps shining his laser pointer in his eye. He's kind of dumb. Okay, so class 3R, we're getting up to 5 milliwatts. You don't want to avoid, but you want to avoid direct eye exposure. You don't want that hitting you in the eye. Why? Because the energy will be delivered before you blink. And that's why we don't want to look at an eclipse. It's because the dimness of an eclipse is actually the problem. You look at the sun and the UV light's going right into your eye, but it's not bright enough to cause you to squint. If you look at the sun now, you go outside and look at the sun, it's bright enough that makes you squint, and that lowers your exposure. You're not blasting your eye. But eclipse is below our normal squint reflex, and so we're sitting there blasting our retinas and corneas with UV light. So we don't want to do that. Now, class 3B or 4, they may damage skin or will damage skin, and so those can be quite dangerous. Here's another kind of laser. This is the ruby laser, probably the first laser, 1960. So we've got lasers for a long time. We've had lasers for a long time. It's brute force, okay? So notice there's no metastable state down here. Whereas the neodymium YAG laser had a population inversion by having atoms up here, and this metastable state was empty, or mostly empty. Whereas the ruby laser is getting a population inversion with the ground state. So you have to have more efficient pumping for a ruby laser because you've got to deplete the ground state. You've got to get all the atoms, or you've got to get more atoms out of the ground state and pump them up here so you can get that population inversion. So that's why we have this flash tube for optical pumping. Look how big the flash lamp is. It's this white tube that goes round and round and round. And basically we have an electrode in here, and it's like lightning in a glass tube. So we put an electric arc through that glass tube and put enormous amounts of light into the ruby rod. And so then this ruby rod right here will get a population inversion, and then we'll have a laser made out of it. And so in order to get that much light into the flash lamp, we have a bulky water-cooled high voltage power supply. Now we can store up that light and get our population inversion and control when the light can come out if we destroy the resonance of the cavity with this thing called a Q switch. And so the Q of the laser cavity, this would be a term for the resonance. And so we can switch the Q on and off. And so if we turn the resonance off, the photons that are emitted here are absorbed or redirected or bounced out of the cavity by the Q switch. And then when we turn it off, then the cavity is resonant. So we can build up a more populated, excited state, and then we turn on the resonance of the cavity, and then the first photon that comes out will cause an enormous cascade. All the atoms or molecules will drop down, and we'll get all of our light burst out in a really short period of time. And so in my graduate days, we had 10 nanosecond pulses. And our laser was, it seemed, if you just looked at the power meter, pretty puny. It was like 0.1, let's see, no, it was 0.1 joules or 100 millijoules. 100 millijoules. That's not very much energy at all. But if it's delivered in 10 nanoseconds, what's the power? The power is equal to the joules per second. Okay, so milli is 10 to the minus 3. Nano is 10 to the minus 9. Okay. And so if we bring that up to the top, if we make this 10 to the 9, okay, see we're dividing by 10 to the minus 9, so we can bring it up on top as 10 to the 9. And so we get rid of that 3, and we can make this a 6, okay. So we've got 10 to the 6, so we have 100 megajoules of time average power. So that's what our molecule feels for 10 nanoseconds. For 10 nanoseconds, it's feeling 100 megajoules of energy. That's getting close to the power output of the Roans Prairie power station. You know, when you go into College Station, you go through Roans Prairie and you see the natural gas power station. It's in the 100 megajoule range. Or megawatt range, I'm sorry, megawatts. And so this is getting close to the molecule feeling the amount of power that's coming out of a whole natural gas power station for 10 nanoseconds. Okay, so it's not feeling it all the time. The Roans Prairie power station is putting out that much energy over time, like continuously when it's on. But this is feeling it for 10 nanoseconds, an enormous amplitude of light. So we get really sensitive spectroscopy signals. Okay, the solid state lasers use this light emitting diode where you have P junction and N junctions and so on, and there's an active region, and you have this this LED light emitting diode in the middle, and then you can partially silver the front and you can silver the back. Okay, so the back side of this, back, not buck, silvered. And so then the laser will come out of the front of this thing. And so that's what we have in our laser pointers and so on, is a diode laser. Super easy to make with our fab techniques, and super low power, and doesn't take a lot. We can run it on tiny little batteries and so on. Well, these are so cheap now, they give them out as like party favors and stuff. We went to a conference one time, it was so fun. And the little gift bag that everybody got for the conference had little laser pointers in them. And you could unscrew the cap and put a little holographic thing in there, so the laser pointer would be like a circle. It was kind of cool. Instead of just a dot, it would be a circle. It could be a line. It could also be a little hand that pointed. So like this little thing would be a little hand that would point. You could point it at stuff. And it had a little spaceship too. And so that's pretty neat. Everybody got one of those. But it was really a disaster for a scientific meeting, because then everybody in the audience had a laser pointer, and they would be like, what about this? You know, what about this? And there'd be little spaceships moving around and everything. And they're like, please put your laser pointers away. And it was really a fun meeting. Yeah. So note to self, that was a great gift, but it was also terrible to have at a conference. Yeah. So here we've talked about the ruby laser, the sapphire laser, and then here's the helium neon laser. It's so strange to think about this. So we excite the helium. And helium's simpler than neon, right? Look at neon. It's got 8 more electrons than helium. And so it's got more energy levels. And so this is so strange. It's collisional transfer of energy. So we excite the helium atom, you know, we make it a 1s, a 2s, there could be a triplet or a singlet state. And so now we have an excited helium atom that bumps into a neon atom. And now the neon atom is excited and the helium atom is not. So we haven't talked about that at all. So we could have an excited electron cloud in helium and it bumps into a neon and neon says, now I'm excited. And the helium is the ground state. And then we pump that helium up again and we get the neons all excited, and then we're making a laser with this state, which is not a ground state, and so we easily have a population inversion right here. It'd be really hard to get a population inversion for helium, but if we put a little bit of neon in there, we can easily get a population inversion in neon with this state. Now, how do we build a laser with that state? The resonant cavity. So we pick a resonant cavity that would match this wavelength of light right here, and that's how we build a laser. So that's the helium neon laser. Now we have lasers all over the place in terms of the spectrum. We have the ultraviolet lasers, visible lasers, near-infrared lasers, and mid-infrared. Now, which of these regions is for our spectrometer upstairs? Like when we do a infrared scan, a FTIR of our organic compounds and so on, what region are we using? I know you can't really see it, and it's in microns anyway. That's probably not going to help you. We do 400 to 4,000 wave numbers. If you convert that to microns, it's right here. And notice there's just not a lot of lasers in that region. And so it would be good to have a broadly tunable mid-infrared laser source for trace and gas phase analysis. So if you want to go into lasers and so on, that would be a great thing for you guys to develop, is a broadly tunable laser, meaning we could scan that bright laser line through the mid-infrared. Now, how could you scan a laser? Well, one way is dimensional. We have the resonant cavity. If we could move one of the mirrors, we're scanning the laser. And so it's just not broadly tunable. We can't scan it that far without difficulty. So now let's look at this. This is a strange laser. It's called an exaplex laser, or some people call them excimer lasers. So exaplex is an excited complex, and an excimer is an excited dimer. And so these are also called chemical lasers. So we'll typically have some chemical reaction, or we'll excite like an atom and have it form a dimer when it's excited. So look, in this case, we have an AB. So we have AB star. So when B is excited, we can form a two-atom complex, or a dimer. And so then we would form, atoms in this lower level. And then when B is not excited, this molecule doesn't exist. So that's interesting. We're guaranteed to have a population inversion, 100% population inversion, because the ground state, or unexcited excimer, the unexcited dimer is not a thing. It falls apart naturally. So it only exists in the excited state. So we have a population inversion. The excited state has dimers, and the ground state does not. And then we put it in a resonant cavity that chooses this particular wavelength of light, and then we have a laser. Now, these are very common. If you've had LASIK surgery, then you've experienced this. This is what they use to produce the UV light that blows out part of your cornea. Okay. We also can do this for knocking things out of the sky or whatever. These are some military implementations of these chemical lasers. So this is a 747 airplane with the whole interior body is a chemical laser. And then it's got this optic thing on the front, and that's for shooting missiles out of the sky. So this is for boost phase, destruction of missiles. So anti-missile defense this can fly near a launch site, and if the missile takes off, it can lock on and shine that laser on the missile as it goes up, burn a hole in the side, and then it blows up. Okay. The problem with this is you got to stay on it for quite a while to burn through the metal shell. Luckily for this particular case, those metal shells are pretty thin because weight is a problem. So if you want this thing to go up quickly, you want it to be extremely lightweight. And so the shell of these missiles is pretty thin and can be burned through. This is one on a C-130 airplane, and they got them on ships now too. And here's the LASIK eye surgery. Anybody had LASIK? Anybody yet? Your eyes are still young. Give it 10 more years maybe. If you have astigmatism, so what is astigmatism? Well, that would be when your eye is not perfectly a spherical lens. Let's say you have like a ridge here. So a ridge will behave like a cylindrical lens, not a spherical lens. And that's what I have. I don't remember what degrees my ridges are, but I've got a ridge in each eye, astigmatism in each eye. If the light is dim enough, then I can see both images. It'll create a double image. And so if I look at like a LED clock and at a fair distance, I'll see the numbers doubled. Okay, and it's from the astigmatism. And so all of the like if they're doubled this way, my glasses will put a cylinder this way. My eye cylinder is this way, my glasses will go that way, and it'll put those images back on top of each other and fix my vision. Or I could go to get LASIK surgery, and they would go in where that ridge is, and they would just blast off parts of it to make a perfectly spherical lens. Now they want to take out the material underneath the corneal flap, and so what they do is they come in, they cut it with a really sharp razor blade and flop it over. And I watched this whole thing. My wife had this surgery and I was watching them do it. So this knife comes, cuts this, they flip the flap over, and then they go in and they reshape the lens of the eye, blasting this, and then they put the flap back on, and then they put a protective contact over the top so it doesn't open up until it like reseals, and then you take the contact off after a few days and your vision is completely fixed. Yeah. And she loved it because she used to not be able to see the clock in the nighttime. You know, she'd look at the side of her bed and she couldn't tell what time it was. And after she got the LASIK surgery, that was the most exciting thing for her. It's like in the middle of the night, she goes, "Oh my gosh, I can see the clock." And she was so excited. So that's pretty cool. I was watching the surgery, and in here in the little like viewing room, I was asking all kinds of questions. They had a little cross-hatched area where the laser would never shoot. I asked, "Well, what's that?" And he says, "That's the hinge. That's this right here." He said, "We don't want to hit that with a laser because we'll cut the flap off. So we protect that area." And also he put a dot here and a dot here. It looked like a Sharpie. I'm sure it wasn't a Sharpie, but it was two black dots. And I said, "What are those?" And he said, "That's so that the computer-controlled positioning, thing that's steering the laser can lock onto the eye, because your eye is moving, every 2 or 3 milliseconds, it's moving. You can't be perfectly still. And so it's moving, and so are the optics, like it's tracking her eye. So I had two views. One was her eye twitching around, and the other view was perfectly still. Well, it never was really perfectly still. The computer was tracking it so that it could lock on and do the surgery. It was very, very cool. I said, how fast can the computer keep up? And he said, the computer is about 10 times faster than your eye movements. So it has no problem keeping up. When the eye moves left, it's moving left, and so on. But he said, if they sneeze, then it's a problem. So the computer knows if it loses track, it stops firing the laser, so it doesn't blast you in the face or anything like that. So that's pretty cool. This uses an argon excimer laser. So argon's a noble gas. It's not going to form a dimer. But if you excite one of the argon ions, then you can form a dimer. So it exists only in the excited state, just like what we're showing here. It's an exaplex. Only in the excited state do we have a diatomic molecule. And then when it spits out its photon of light, it's now 2 argon atoms. And so you can't have a ground state. You only have excited states. So that's how they get the UV light out of it and the population inversion. Okay, and then we get into huge and little lasers. This facility is the most powerful laser in the world. And it starts with this diode laser. This is a little neodymium YAG laser, and you can see the penny is in there for scale. And then this is a facility that's like 3 football fields long, and it's a single laser plus 92 laser beams. This is a worker here for scale. This is how big this facility is. Okay, and it's Lawrence Livermore's National Ignition Facility. And so I'm going to play this video, but I'm going to stop the lecture so I don't get a copyright strike. So go to this video. Just go to NIF, type in, if you're online, type in NIF laser and go look at the Ride the Beamline videos on YouTube.